All right, assalamualaikum and very good. I think you can all hear me. Very good morning. So for today's week, we're going to talk about geometric dimensioning and tolerance. So this previously we talked about line types. That was in your assignment one. So today we are going to talk about um, geometric dimensioning and tolerance, how to understand the purpose of geometric dimensioning and tolerance, and recognize the symbols and also the geometric dimensioning tolerance. Now, where are we? Geometric dimensioning and tolerance is like taking back any high school English. Okay, that is correct. Learning Gd&T, short for geometric dimensioning and tolerance, is like exactly like learning a new language. So this is very important, especially when dealing with um, understanding what people's base drawing standard are. All right. So in order to describe geometric dimensioning and tolerance, we require to define the geometric requirements of the part and the assembly geometry. Number one. Number two is to define the allowable variation in the form and possibly size of the individual. And the third one is to define the allowable variation between the features. Now, we usually use high school, if you remember, you use chemistry periodic table, right? Now, for today, we are going to use the same thing, but we are going to use FOPRL. Okay, what does FOPRL stands for? We are going to explain that later on. This section starts looking at the 14 Gd&T control symbol first, and then we will use this technique FOPRL to develop a similar concept as the periodic table. Now, if you remember the periodic table, it's like example of a high school chemistry where you have an element columns and row of both elements, and each box has information about the elements. For example, if you take TC, what does TC means? It's a symbol. Okay, TC is a symbol. And then on the top left is 43, which is an atomic number. On the right side is an atomic mass, and then you have an electron figure configuration, as well as an oxidation state, and then the melting point 2140, and also the boiling point, as well as the density and electromagnetic negativity. So each element has their own information, and we are going to explain that also in Gd&T as well. But for periodic table of Gd&T, you have 14 columns. Okay, you have a row column and 14 boxes. 1, 2, 3, 4, 5 on the top, 5 on the top, 5 on the bottom center row, 3 on the third row, and last one is the cylindricity, which is on the last row. So this is how the periodic table of Gd&T symbols. So each box has their own information. For example, you have on the column of form, you have straightness, flatness, circularity, cylindricity. On the column of orientation, you have parallelism, angularity, and perpendicularity. In the center, you have profile, line profile, and surface profile. On the runout, you have circular runout and total runout. And finally, on the location, you have position, symmetry, and concentricity. For the FOPRL, form, orientation, profile, runout, and location. So on the box on the left side, top left side, which is a C, stands for whether the total white tolerance zone can be modified to a cylindrical shape. All right. And then on the right side indicates whether the datum is required or not. The bottom side Z indicates the total white tolerance zone shape, and the last on the bottom right side indicates the ASMEY 5M 1994 a standard, which is the section that describes the control of it. And on the center, you have a symbol and a name. So each control will place information as a someone, like the same as in chemistry symbols. So five kinds of geometric controls. Okay, these I explained to you already. Form, on orientation, profile, on out, and location. First is form. What is form? Okay, it's the first kind of geometric control we look at. It's a simple of form. Form is just like it sounds. Okay, so form dalam bahasa Melayu dipanggil bentuk. They control the acceptable variance in the shape. For example, straightness ataupun kelurusan. Why is a two-dimensional, and what is a two-dimensional and linear? A straight line, of course. Let's call the control a straight line. So the straight line can be straightness. The icon represents a straight line. That will be a line, a straight line. Here it is. Next is a flatness. It is a three-dimensional. Compared to the straightness, it has three-dimensional and linear. So it is a flat plane. Let's call it a flatness. So the icon represent a flat plane would be a shape of a plane. Alright? It's a shape of a plane. And then another one is called a circularity, which is a geometry with two-dimensional and a rotation on rotary in nature. Let's call the control of a circle circularity. Alright, because of its circleness. And for a three-dimensional, we call it a cylindricity. And its nature is rotation, but it's in a cylinder, so we call it a cylindricity. The icon represents a cylindricity is a shape of a two parallel line and a circle inside. So let's look at this one. On the first left, the top left, we have, if you look at this line, it is a straightness of 0.003. On the right side, you have a flatness of 0.002. On the bottom side, you have a circularity of 0.002. And this one, you have a cylindricity of 0.003. Form. Okay, form call out. So these are the four form of these are the four form, the form of four form. Okay. Second one, the orientation controls. The second kind of geometric control that we look at is the next simplest, which is the orientation. Orientation is just like it sounds. Orient, berpusing, berpusar. Right? There are three kinds of orientation control. I remember thinking about my arm swinging. Okay, if you swing your arm like that, you can see your arm is orient on the horizontal. So if you go like this, it's a orient on the vertical. So the first orientation is angles. So when your arm is in a horizontal, like this, it is at zero. It is parallel with the ground, right? It is a parallel with the ground. As you rotate your arm, the angle sums an arbitrary angle. Where your arm is pointing up, what is the angle it is formed with the ground? Of course, when you're pointing up, it's 90 degrees, okay? Because it is perpendicular to the ground. Another one is parallelism. What orientation is the 0 degrees from parallelism? So basically, the icon represent the thing should be parallel would be two parallel lines. So the first one you have, previously you have angles. The second one you have parallel. So the third one will be angularity, which you have what orientation is an angle? The answer is angularity. So the icon to represent two things. One is let's say a horizontal line. The second one is an angle. You have an arbitrary angle that looks like an angle. Finally, you have a perpendicularity. The perpendicularity is an orientation at 90 degrees from the reference, which is a perpendicularity. And the icon is like the same thing. You have one horizontal line and one vertical line. So you have four. The first one on the left side, you have a parallelism. of 0.5 at point datum A, a perpendicularity of 0.5 at datum A. All right, it's a perpendicular. This one is parallel to datum A. An angularity, okay, of 0.4 height or 40 degrees at an angular or datum A. So you have three. Another one is, of course, no, three actually. Parallelism, angularity, and perpendicular for the second orientation. The third one is we look at the profile control, right? The profile control is just like also the same as it is. They control the acceptable variance. So, for example, if it's a complex variant, what happens? A contour, for example, or concavity or convexity of a car. It can be actually simply explained as a line or circle. All right. So let's look at the first profile control. The first profile control, profile control is the line. We call the line a two-dimensional profile or a profile of a line or line profile. The line in question can be any shape or any number of lines and arcs. And the icon used to represent a line is like a shape of it, right? A line. The second one is a surface, which is a three-dimensional. It has a surface profile where the line doesn't have a surface profile. So combining the shape of a line from left to right, you have a surface. So this is look at two examples. The first one, this one is a what? A surface profile of 0.5 from datum A, right? So you have two, line profile and surface profile. Now we look at run out. Let's continue looking at the complicated geometry of run out. Okay, run out controls same thing and just like it sounds. They control the acceptable variance in a revolve feature. So revolve is what? Like a vase, for example. Example of a tire, right? It's revolving. A battery. A battery is also a cylinder, but it revolves in the center. Now next, the first revolve, sorry, the first run out would be called the circular run out. The icon used to represent a circular run out is one arrow. Note that this symbol is like a needle from a dial indicator and that's exactly how we measure it. And the second one is called a total run out, which is a three-dimensional control of total run out. It used to represent a circular run out. This is perfect time to talk about what we call a rotation or dial indicator over feature. For example, we have a diameter of 1 with a tolerance of 0 to plus 0.0 to minus 0.02. This is a cylindrical. So a total run out of 0.001, okay, total run out of 0.001 within datum A, right? That's how you say it. And lastly, we have location. Location is the last kind of geometric control we look at in the next most complicated location. The location control is just like it sounds. They control the acceptable variance in the location of the feature. There are three kinds of location control. Okay. The first one is position. The obvious location control for features. Of course, they call it location. So basically, position number one. The icon represents where the feature should be, right? The second one is symmetry. The first non-obvious location control is symmetry. The icon represents two things. The first one should be symmetry. And the icon is like a mirror, a reference line to a datum and two little symmetrical lines. The third one is coincentricity. This is most obviously known as because of its has the same center axis. Okay. And finally, a call out. A call out. Sorry, three only. The position, symmetry, and concentricity. So let's look at example of this. All right. A position, okay, a reference has a position at 0.12, position of 0.125, okay, between A, okay, 0.125 between A and B, right, between A and B, okay, maximum, at maximum. So a maximum value between A and B only 0.125. So you can go from 1.5, but sorry, 0.15, 0.15, but a maximum of 0.12. Okay, that's how you say it. So these are all the complete 14 FOR FOPRL time tables. Okay, FOPRL tables that you need to memorize. Now let's talk about how we can explain it in a sentence. Okay. ASME 14.5 1994 defines a feature as a general term applied to a physical portion of a part, such as surface, pin, tab, hole, or slot. So in other words, anything related to these four mentioning, okay, might be explained as a feature. Right. What is a size? A size is a form. The general term of a size is, this is what you measure on a part. Okay. For example, the size of its length, the size of its height, the limit of it, the maximum size, the minimum size, the number of found in the size, the nominal size, okay, designated size. A feature of a size example, for example, one cylindrical surface, one spherical surface, two set of opposed elements, set of opposed parallel surface. An example of a measurement device that can be used with is called a caliper, which has an outer and inner diameter, and also a depth gauge. So why are the features of size very important? It's most of because the feature can be modified according to the size of the feature. Everyone knows that engineers love to modify things, so you need to have a modification. So for example, you need to have a tolerance in between a maximum or minimum. If you cannot go from higher or lower than that. So a circle, for example, on this side we have S, M, L, and F, represent a lot of things. The first one, it regardless of the feature size, RFS, or the maximum material condition. This also LMC, and also a free state. Okay. So regardless of size, is a presentation of S. The maximum material condition represents M, LMC, and also free state. So regardless of feature size means, but that there is the default if no modifier is given. The tolerance zone is not affected by the actual size, right? So the size of the tolerance is very small. So we're talking about tolerance right now. Just because you don't see the symbol does not mean the concept is actually used, right? The maximum material is the allowable, the allowable maximum material you are allowed to use. The bonus tolerance, for example, the thickest plate, the smallest hole, right, is stated as M. The least material condition, which is the most rarely used because you need to have at least, example of a thinnest plate, the largest hole. The free state is a term used to describe a part after removal of a force applied during, for example, a car that a pintu kereta, you push through the door towards the chassis, right? or flexible part, for example, rubber gasket, wire form. Okay, when you have force onto it, it may react to the force and change its features. So the tolerance zone and shape, the next stops of Gd&T primer train is the tolerance zone and shape station. These sound like the same thing, but they are two different things. Let's start with the easy one, the zone. So the total white zone tolerance. Okay, all control have total white zone tolerance except for concentricity because it's already in a concentricity shape. Only 5 can have a cylindrical tolerance zone: position, orientation, and straightness, parallelism, angularity, and perpendicularity. Alright. Concentricity requires cylindrical tolerance zone. Okay. This is a tolerance zone symbol. 0.14. Total white zone is, unless you put the diameter here, it becomes a cylindricity. Alright. So now you know a couple of things inside this box already. You have this one is parallelism, total white zone of 0.14, maximum material condition, U is the datum, position, you are put the diameter here, so it's a total cylindrical zone of 0.002 with least material condition at point Y. Alright. So datums. Do one simple thing. Datums are a way for the part designer to tell the part inspectors how to hold and immobilize the part during the inspection. So the datum is like a point. Okay. Kat mana kamu pegang, kat situlah datum. It is a reference. Right. For example, point, axis, plane. It is an origin. Okay. A location where you want to show where it points. So the standard only calls out 3 letters that cannot be used as datums. I, O, Q. Why? Because does not have to start with, the standard doesn't. Why? Because the standard does not say you can have to start with A and go in a particular order. I prefer never to use S or Z. Okay? For example, you don't use 0 because it mostly refers to the center axis. Okay. Q or similar to 0. It has a 0. I is an index. So, what does it mean? Number 1. The datum is the bottom surface. Okay, if you look at the picture here, you find that the datum is on the bottom surface. The datum is not a feature of size. Alright, it doesn't have any feature of size. The datum simulator can be a gauge plate, and gauge plate needs to be 10 times flatter than what you have to check. So basically a datum is 10 times flatter than what you want to check. So number 2, what is datum? This datum is the center axis. Okay, it is a center axis. This datum is a feature of size. It is also a feature of size. And the datum simulator is a 2-piece clamp. RFS, when the clamp is squeezed tightly, the maximum material condition MMC is a fit size. So, regardless of feature size, clamp squeeze, maximum material is when the clamp is fixed size. So, in a basic dimension, basically the dimension of the tolerance, okay, is boxed. Like for example, at the bottom here, you can see it's 0.500. The basic dimension don't have a tolerance. They are used by other geometric dimensional. So basically, it doesn't have any more tolerance. It is used by another dimension, right? Next, angular basic dimension. An angular basic dimension, does it have a tolerance? Does it have a tolerance at a 40 angle, a degree angle? All right. It certainly does. Okay, it certainly does. It's also in terms of a size, right? But not in terms of an angle, but a size. A position basic dimension. For example, this one, you have a position A is position between B, for example. A has a position of between 1.5. Okay, it's a position of 0.12, for example. 0.1, 0.02. Okay, so it's about the size of in between 0.005 to 0.00. Finally, a profile basic dimension. Profile basic dimension, does it have a dimension as well? Yes, it does have a dimension. This is the dimension. Okay, it's a 0.5. It is about 0.5 of a tolerance. So what's coming up next? Now we are going to see an example of this geometry dimensioning and tolerance in a sentence. Okay, look at this one. The 14 geometric to the tolerance of the dimension. C at between C and B and D, maximum material condition. So you read something from left to right. Don't skip anything. The first bar has a template already. The first bar has a template which the feature shall be or have a blank geometric characteristic. The second bar, within a total white tolerance zone of cylindrical tolerance zone of a full indicator movement, blank geometrical tolerance at a modifier. The third bar has with respect to datums, and lastly, stop. Okay, let's look at an example. The feature shall be, okay, the first box, angular, within, line is within, a total white tolerance zone of 0.014 at least material condition with respect to datum G. So you have, let's do this exercise. All right, let's remember this one. You have straightness, symbol, tolerance, and a datum. I think you should write, okay, if you want flat, this is a flat, with a total white tolerance, second point of 0.0, what? This is not 0.2, right? This is 0.03. Okay, so the first one is 0.03, 0.02. The second one, is the feature shall be angular, so it has an angular within a total white tolerance, of 0.008 with respect to datum D and F. The third one, the feature shall have a surface profile with a total white tolerance zone of 0.002. The feature shall be asymmetric within a total white tolerance of 0.004 with respect to datum F. The feature shall be positioned within a cylindrical tolerance of, this is a position, cylindrical tolerance of 0.001 regardless of feature size with respect to datum B. The feature shall be straight with a total white tolerance zone of 0.002. The feature shall have a total run out, this is a total run out, with a full indicator movement. Because it is a total run out, so it is a full indicator movement of 0.005 at respect with datum XM. The feature shall be perpendicular within a total white tolerance of 0.007 at maximum material condition with respect to datum C. The feature shall have a line profile within a total white tolerance of 0.003 with respect to datum C, B at maximum material condition, and D. And finally, The feature shall be parallel within a total white tolerance of 0.009 at maximum material condition with respect to datum E. So that is all for geometric dimensioning and tolerance. I want you to memorize this, and I want you to take this very importantly, because we're going to do some exercise. If you want to read to full detail, you should know what Gd&T is. You can do practice with this. I will upload this slide. Okay, you can read this, all of this. The feature shall be parallelism within respect to total white zone of 0.02 with respect to datum A. All right, so you have to, you can practice with this, all this practice up. So the wrap up, I should say, is you should, number one, you have to remember 14 Gd&T symbols and the FOPRL. The second one is you have to remember the S, M, L, and F feature of size. The third one is datum and the tolerance zone shape, as well as the reading feature control frame. That's all for today. Thank you very much. I will see you soon. I will upload the quiz or an assignment later on for us to for you to do. Okay, thank you. Any questions you can raise in the WhatsApp group.